So today, we're going to dive into a really fascinating new paper that proposes a radical new way to solve one of the biggest mysteries in all of science. And get this, it's a story that involves dust, a very weird kind of ice, and the fundamental laws of gravity itself.
All right, so let me start you off with a question that sounds like the beginning of a really weird joke. What are the tough outer shells of pollen, a rare form of ice that can exist at room temperature, and the force that holds the entire universe together all have in common?
And the answer, believe it or not, isn't a punchline. They are, in fact, the key ingredients in a brilliantly clever new experiment. An experiment designed with one very ambitious goal in mind. Their goal? Oh, just to solve what is arguably the biggest, most stubborn mystery in modern physics. A problem that has stumped some of the greatest minds for pretty much a century now.
So before we get to the experiment itself, we've got to open up the case file on this mystery. At its heart, it's a fundamental conflict between the two most successful theories we have ever come up with to describe our universe.
On one hand, you've got general relativity. That's Einstein's masterpiece, right? It describes the universe of the very, very big, planets, stars, galaxies, as this smooth, predictable, curved fabric of spacetime. But on the other hand, you've got quantum mechanics. This is the law of the very, very small. Atoms, particles, all that stuff. It describes reality as this fuzzy, chaotic world of probabilities and really strange connections. The problem? They absolutely hate each other. The math just completely breaks down where they should overlap. It's like having two different conflicting rulebooks for the same reality.
So for years, physicists have been playing detective on this case, and they thought they had a really promising lead, a smoking gun test that could finally tell us which description of gravity is the right one deep down.
And the idea was super elegant, really. It's based on this thing called quantum entanglement, what Einstein famously called spooky action at a distance. The thinking was if you could get two tiny objects to become entangled with each other using only their gravity, well then, gravity itself must be quantum. Case closed, right? But then, a huge plot twist. Recent work, and this is cited directly in the paper we're looking at, showed something pretty startling. It turns out that even a classical, a non-quantum theory of gravity can actually create entanglement when it interacts with quantum stuff. So what this all means is that just seeing entanglement, well, it's not the smoking gun everyone thought it was. It doesn't prove gravity is quantum. The original clue has gone cold. The detectives are back to square one, and they need a much, much smarter way to investigate. Okay, and this is where things get really interesting. Instead of chasing that old, cold clue, this paper proposes something totally different. A brand new angle, a radical new lead. What if there's a hidden signature, some subtle effect that nobody's ever looked for before? The paper calls this new idea information pressure. Now, stick with me here. Imagine a super packed crowd of people, and they're all linked together somehow. If they all suddenly shift in a coordinated way, they could create a real physical push, right? Well, the idea here is kind of similar, but on the quantum level. In places with incredibly dense and complex quantum entanglement, the very structure of all those connections could create a tiny, almost imperceptible physical push, a force born from pure information. So this theoretical force, this information pressure, is the freshly the detectives have been desperately looking for. It's a signature that, if the theory is right, would only exist if gravity has a deeper quantum nature. If they can just find a way to measure this incredibly faint push, they might finally crack the case. Okay, but how on earth do you even begin to measure a force that's supposed to be almost infinitely small? You can't just go buy the tools for that. You have to invent them. And the toolkit this paper proposes is, frankly, ingenious. The whole strategy really boils down to three super clever steps, each with its own special device. First, you've got to trap light. Then, you've got to tune a quantum spin. And finally, you have to witness the force itself. Basically, you need a way to trap light to amplify the whole interaction, a way to create and hold a stable quantum state, and then a super sensitive witness that can actually feel the tiny push they're looking for. And for the first part of this toolkit, device A, you're not going to believe this, they're turning to pollen. Yup, they suggest using sporopollenin, the incredibly tough outer shell of pollen grains. If you coat these on a prism, their microscopic structures act like a natural hall of mirrors, trapping light and bouncing it around for way longer, which helps amplify any potential effects. Next up, device B, the spin gate. And again, they're looking to nature for inspiration. You know how some birds can navigate using the Earth's magnetic field? Well, the theory is they use molecules called cryptochromes. This experiment proposes using molecules that mimic those, acting like a tiny quantum compass to hold a delicate quantum state stable for a really long time. And finally, we get to the real heart of the experiment, device C. This is the witness. It proposes using magnetized dust particles trapped inside a thin layer of ice-21, which is this bizarre, high-pressure form of ice that's actually stable at room temperature. This whole dust-ice combo acts like a quantum bus, connecting the light and the spin states. And most importantly, it's designed to be sensitive enough to physically move if that tiny information pressure force gives it a nudge. Okay, now this next part is what I think makes this whole idea absolutely genius. It's not just about the clever tools, it's about the philosophy of the experiment itself. It's designed to give us a definitive answer, to help close the case, no matter what the result is. So you might be thinking, okay, but what if they build all this fancy stuff and find absolutely nothing? No tiny force, no signal, just noise. Wouldn't that just be a huge failure? Not at all, and that's the beauty of it. That's the whole point. The experiment is designed with what the author calls strict, predefined pass-fail gates. This isn't just a vague fishing trip. It's a super disciplined process designed for a clear result. And we're not talking about vague goals here. Look at this. They have hard, numerical targets for every single piece of the puzzle. The bioprism has to trap light well enough to hit a quality score over 100,000. The spin gate has to hold its quantum state for at least 100 microseconds. And the witness has to be sensitive enough to detect an acceleration that is just mind-bogglingly small. If any of the parts fails to meet its target, they know exactly what needs fixing or rethinking. So you see, this whole thing is set up as a scientific win-win. If they find a signal that matches the predictions, it's a monumental discovery. It would be a huge boost for the whole idea of quantum gravity. But if they find no signal, and all the parts worked as well as they were supposed to, that's also a huge success. It would prove this particular theory is wrong and put up big red flags for future theories, telling all the other detectives where not to look. Either way, science moves forward. So, what's the big takeaway here? It's that maybe the next giant leap for physics won't come from a collider the size of a city. Maybe the answers to the universe's biggest questions will come from a clever tabletop experiment, born from the creative combination of biology, chemistry, and a little bit of dust. It just leaves you with this one kind of wild thought. After a century of searching, could it be that the clue to solving the biggest mystery in physics, the very nature of reality, isn't out in the cosmos, but has been hiding right here on Earth this whole time, inside something as humble as a single speck of pollen?